Hello guys, welcome to the channel. Today I have a really fun trig integral for us to try, so let's break it down. Cool. So the story behind this integral is I found this integral online, but it's a little bit on the easier side and a bit quick, and it wasn't something with enough substance to make a video out of, so I thought to just try and integrate the reciprocal of that. So I've just flipped the fraction over. So this is what we'll be trying today, and I'm just going to pause for a moment for anyone who wants to try it. Cool, so let's dive straight into it. So I think it's quite important to recognize that we have different subjects inside our trig functions, which is really annoying. We have a x here, and then a 2x on the bottom. So we want to try and have everything either as 2x or have everything as x. And we can use double angle formulae to try and solve that problem. So if we can sub out cos 2x for cos squared x minus sin squared x. Just like that. So our cos 2x is subbed out. Perfect. And this is actually a difference of two squares. That's a good pattern to recognize, which means you can factor out like that. And now we have common factors on the denominator and numerator, which we can just cancel out. Perfect. So now we're left with this integral, which is a lot easier to deal with. But we now have a new problem, which is we have two trig functions on the denominator. And it would be really, ideally, we would want to have one trig function on the denominator, especially since it's only a constant here. So we can try and use double angle formulae again. And what we can try and recognize the pattern is that if we say that x is a, we have a cos a and a sin a, but we're trying to look for a cos b and a sin b to sub in so that we can use cos a plus b or cos a minus b instead of two separate integrals, so two separate functions. So we can try and write in this form, and this r here is here because we need to make sure that we have a magnitude of between minus 1 and 1 with these trig functions, because that's the range of sine and cos. So all I'm doing is taking the coefficients of cos and sine, which is just 1, and applying Pythagoras. And there you go, so you get root 2. We can chuck a box around that, that's really handy. And we can just sub in our root 2 for r, just like that. And what we can then do is we can factor out root 2 on the right hand side. So look at that. And so now we have 1 over root 2 here and 1 over root 2 here. So if you multiply them back in, it's still the same function as the previous step. So we've not actually changed any values, but we just factored out smartly. Cool. So now what we need, looking at this equation here, is we need a value where we need sine alpha to equal cos alpha to equal 1 over root 2. So that for this to hold true for the cos b and sine b. There you go. So really handily, when alpha equals pi over 4, this is true. And so that means then we can sub that in for our alpha. So now we have root 2 cos x minus pi over 4 is equal to cos x plus sin x. And so these guys are identical. And that's really important. So we can chuck a box around it. And now what we can do is we can sub that in. So instead of cos x plus sin x, we have this guy. And it's a lot easier to work with. We can take out the 1 over root 2. And I've just wrote this as sec, which is just 1 over cos. And now our lives is a lot easier because we only have one function. And from here, some people may recognize that the identity and just know that when you integrate sec, it will produce ln sec plus tan. But for anyone who doesn't know that, we can work through it together. Cool, so here's our problem. And there's a really nice trick to spot when you're integrating sec, which is to multiply both the denominator and numerator by sec plus tan. So it doesn't change the value because we're timesing and dividing by the same value. And when you simplify, we get this guy, which is sec squared plus sec tan over sec plus tan. And this is really handy because we may be able to then recognize that we can use this formula, which is if we have a function on the denominator and its derivative on the numerator, when we integrate it and times it by some kind of constant, it should equal the natural log of the function. So that's really handy to see, because when we differentiate tan, we get sec squared, and when we differentiate sec, we get sec tan. So that's really handy. So we can try and work backwards since we know our function is sec plus tan, just like that. And I'm aware that in our integral we have x minus pi over 4, but I've just put x to save space and because it doesn't affect our answer. And if you think about it logically, we're just moving the function a bit to the left or a bit to the right. It doesn't actually affect the integral. So it's important to remember to have x minus pi over 4 in our final answer, but just to save space, I've just have x here. Cool, so if we set y is equal to our function, natural log of sec x plus tan x, we can then say u is equal to sec x plus tan x. We're using a technique called chain rule, which is adding another variable in between y and x to try and make our lives a bit easier. And whenever we add a new variable, we should chuck a box around it because it's quite important. Cool, so then we can write y in terms of u. So I've just subbed out this sec plus tan for u. And then it's very easy to find dy du is just 1 over u. Perfect. We can chuck a box around that guy as well. And then now if we just differentiate u, so you have then du dx is equal to sec x plus tan x plus sec squared x. And this is kind of what I said earlier. These are kind of just good identities to know. But if you don't know them, you can prove them using quotient rule, which is this equation. But I'm not going to get into that because it's something quite relatively trivial, I think, relative to the problem we're doing. So if we carry on, so now all we need to do to find dy dx is just to multiply our derivatives, and the du's you see will cancel out and we'll be left with dy over dx. And we've just multiplied 1 over u and what we have here. And all I've done now is I've just subbed out for u sec x plus tan x. There you go, just like that. So you can then see dy dx is this guy. And it's really handy because we were looking for a constant and we can see that we've got exactly in here what's in our integral. So we don't need to multiply by any constant, so we could just say that k is equal to 1. Because we don't need this constant, because this is perfectly holding true. Cool. So now we can say that this long integral, and just remembering to put x minus pi over 4 in here instead of x, will equal this guy, which we've just shown by working backwards and differentiating this guy. Cool. And yeah, so now what we need to do is we just need to sub in our bounds to produce this calculation. And I've just wrote pi over 4 here because pi over 2 minus pi over 4 is pi over 4. And here 3 pi over 8 minus pi over 4 is just pi over 8. Perfect. And so we can then, if you plug into a calculator the trig values, this is what you'll get. You might not get the exact form, you might get decimals, but that's okay. You can then simplify it to this natural log, and that is our answer, so we can chuck a box around it. And also just quickly, if your calculator doesn't give you an exact value, I have the answer here to 5 decimal places. So as long as you get something similar, I'm aware maybe it's a bit hard to copy the exact value, but as long as you're getting something similar to that, then you probably got it right. There you go. So that's the integral. I really do hope you enjoyed the video, and I look forward to seeing you guys next time.